In this video, we're going to review what we've learned at GCSE about ionic bonding. So what is an ionic bond? Now at A-level, we need to be very precise with our terms. So remember, we've got these key definitions that we can put onto our glossary. Ionic bond is the electrostatic, so that just means to do with charges, positive and negative, attraction between oppositely charged ions. So we've got a positive ion and a negative ion, and they're going to attract each other, and that's going to result in the ionic bond. Now that is the bonding. We'll come later to what the structure is called. So remember, in our video for metallic, we reviewed the structure and the bonding. We need to do the same here. So the bonding is ionic bonding. It occurs between a metal from the left-hand side of the periodic table and a non-metal. So when you have a metal and a non-metal, and we've reviewed this already in the introduction pack, then we're going to get ionic bonding. And what happens is electrons are moved, they're transferred from the metal, who loses their outer shell electron, to the non-metal, who gains to complete their outer shell. And that forms positive and negative ions. So the metal ions lose electrons and become positively charged. So remember, sodium becomes Na+, Mg becomes Mg2+, and the non-metals gain. So chlorine becomes a chloride, Cl-, oxygen becomes an oxide, O2-, so they gain and become negatively charged. They gain to complete their outer shell, so we can get a noble gas configuration. So let's just remind ourselves of what we would have done at GCSE. We're going to draw a diagram showing only the outer shell electrons. So we're not going to show all the shells. So let's just remind ourselves. You could pause the video now and remind yourselves of the electron configuration, the full electron configuration of a sodium atom and a sodium ion. So maybe pause the video and think, how would you do it? 1s2, that kind of thing. How would you do it? So if you did that, you should have got that there are 11 electrons in sodium. It goes into the third shell, the last electron in the S subshell. So it goes 1s2, 2s2, 2p6, 3s1. Our outer shell electrons, so our third shell, has just got this one electron in it. So if we say we've got a sodium, and then we're just drawing the outer shell, remember? So we're going to just draw a circle, and we're going to put one electron on the outer shell. So if sodium were to lose that outer shell electron, because it's a metal, we can see it gets noble gas configuration, P6 configuration, by losing the third shell of electrons. And so when we draw that Na with that circle to show that outer shell, then that circle has lost that one electron, so there are no electrons now on this third shell. And we would put this in a bracket to represent that we're going to put a charge on it, but the charge is on the whole thing. So there's a 1+ charge, Na+. So when we write sodium ion, we write Na+. When we write sodium atom, we just write Na. So we can do the same for chlorine. You could pause the video and do the electron configuration of chlorine. So if you did that, you should see that the chlorine atom ends 3p5, 17 electrons, and the chloride ion gains an electron. Notice that we've underlined IDE, chloride. When atoms become positive ions, they don't change their name. You just write sodium ion, magnesium ion, potassium ion. When negative ions gain electrons, they become negative ions, we get IDE, so chloride, oxide, fluoride, phosphide, nitride. If it says ATE, it is also a negative ion, but it contains oxygen. Now we're not doing those right now because we're just looking at simple ionic bonding between a metal and a non-metal. So chlorine, outer electrons, so we need to remember that the outer electrons is everything in the third shell. So we're doing the outer shell electrons, not just the subshell. So there are 7 electrons in the outer shell. This is a dot and cross diagram, so I've already used crosses, so I'm going to use dots. So I want 7 electrons on chlorine's outer shell. So I'm going to go around putting 1 in each orbital first and then pairing up afterwards. So I've got 7 electrons there. And then when it becomes a chloride ion, it gains an electron from somewhere else, in this case probably the sodium. And we would say we've got the 7 that we had before. So the 7 dots, and then we've got that 1 cross. And because we've got 1 extra electron from somewhere else, we're a 1- ion. So it's in group 7, so it's got 7 dots, and then it's gained to get a full shell, so it's got 1 cross to give it the 8 electrons, and we give it a 1- ion. Now, how do then these sodiums and these chlorides, when they attract each other, how do they line up inside the ionic lattice? And what we find is, a bit like metallic, they arrange themselves in a regular pattern. We call this a giant ionic lattice. So regularly, endlessly repeating, and this is our structure. So remember we said we're going to need to refer back to their structure and their bonding. So their bonding was ionic and their structure is giant ionic lattice. And now we need to arrange our sodiums and our chlorides in our regularly repeating pattern. So we're going to go sodium ion, yeah, and then we're going to swap and we're going to draw a chloride ion. Now chloride ions are a little bit larger than sodium ions, so I'm just going to go a little bit minus, a bit bigger for the -1, and then repeat sodium. Oops, did that in the wrong pen. Just do that again. Sodium, and then on this line, notice how it's alternating. So it's a regular pattern of plus, minus, plus, minus. I just draw that extra minus in there. Get these 9 ions in there. This is our pattern of Na plus ions attracting Cl minus ions. And we could look at the next layer. If we looked at the next layer, it would be alternating. So it would be the next layer on top. If I just do that underneath, would have minus, minus, and then plus in the middle. So we would end up with the opposite arrangement. So the top line so the minus would be on top of the plus. Now, we can then draw that if we want in a kind of cubic pattern. My drawing isn't great, so I am just going to sketch out the sort of shape of a cube roughly. So I'm just kind of like the shape of a cube roughly in a kind of pencil that I can draw over. 3-dimensional drawing is not my strongest thing. So now I'm going to draw over it. So I'm going to go plus ion. But the next one next to it, on this top right corner, can't also be plus. The one at the back could be plus. The one at the bottom front could be plus. You see, you have to alternate. So in a 3-dimensional arrangement, we can see that each positive ion, so each Na plus, is actually surrounded by 6 Cl minus ions. It's got 1 in front, 1 behind, 1 above, 1 below, 1 to the left, 1 to the right. So it's got 6 all around it. So this is a giant ionic lattice. So we had metallic bonding, giant metallic lattice of positive metal ions with delocalized electrons, giant ionic lattice, positive and negative ions attracting each other, opposite ions next to each other. So we can go a little bit further with our ionic bonding and then tie it back to our formulas that we did earlier on. So just remember that from our periodic table, if you're in group 1, you have 1 outer shell electron, and then you would lose that to become a 1+ ion. If you're in group 2, you have 2 outer shell electrons, and you would lose both those 2 to become a 2+ ion. Group 3, you would lose 3 to become a 3+ ion. Then we've noticed we've missed out group 4 because things in group 4 tend to form covalent bonds, not ionic. If you're in group 5, you have 5 outer shells, so you don't tend to lose 5. Group 5 things tend to be non-metals, And so they would go to the right, they would gain 3 to get to 8, and they become 3 minus. In group 6, they would gain 2 to become 2 minus, and in group 7, have 7 outer shell electrons, so there'll be 1 gained to become 1 minus. Just some notes, boron is in group 3, and boron is a non-metal even though it's in group 3. It's the only non-metal in group 3, so it doesn't form ions, it forms covalent bonds. Carbon and silicon in group 4 form covalent compounds, don't usually form ions. Tin is normally tin 4+, but it can be 2+ as well. You'll get Roman numerals, as you will for lead as well. So you'll get told for tin, lead and transition elements, you'll get these Roman numerals. But remember that we have to remember that zinc is always 2+. And silver is always 1+. So we just have to remember those two transition metals. Otherwise, we're going to get Roman numerals if they don't live in a group that we can easily identify. So let's put that into practice. It'd be really good for you to just pause the video, think about each one of these in turn, and have a go at drawing the dot and cross diagram from your GCSE experience before watching the solution. But you could pause it after each one and check that you're doing them right. So sodium and chlorine make a compound called, so the metal keeps its name, sodium, but the non-metal becomes the ide, so sodium chloride. Now we're supposed to be able to figure out the formula for sodium chloride. You could do the dot and cross diagram first if it helps you figure out the formula, or you could remember that sodium ions are Na+, chloride ions are Cl-, so we're going sodium chloride, and then we're going to draw a dot and cross diagram. So my tip for you is the metal always loses its outer shell electrons, so it ends up not having any outer shell electrons, so you don't need to draw a circle around it, just Na in a square bracket to show that the plus is on the whole thing. So the metal, sodium was in group 1, it lost 1, we gave it a 1+ charge. Chlorine is in group 7, so we're going to draw a circle around it. We're going to have 7 of one type, so I'm going to do 7 crosses, just a bit easier. 7 of one type because it's in group 7, and 1 of the other type, that gives it the 1- charge, so it had 1 negative charge because it has 1 dot, 1 electron from the sodium. Magnesium and fluorine is going to make magnesium fluoride. Now, if we remember that magnesium is in group 2, so it's a 2+, but fluorine is in group 7, so it's a 1-, then we know the formula must be MgF2. So why is that? So Mg, metals lose their outer shell electrons. They get a charge equivalent to their group number. The non-metal, fluorine, is in group 7. So we can draw that circle around it. We can put 7 crosses because it's in group 7. And 1 dot, because it gains 1 to get a full shell. That's why it's 1-. Now there was 2 fluoride ions. Now the little 2, it was down 2 in the formula. So in a formula, the numbers hit the floor. But because here we're not showing a formula, we're showing what it's composed of. It's a bit like an ionic equation. We need 1 Mg2+ and 2 fluoride ions. So we put the 2 in front. We've got 2 fluoride ions. When we're making the formula, the numbers hit the floor. And so it's MgF2 with the number down. Sodium and oxygen is going to become sodium oxide. So sodium's in group 1, but oxygen's in group 6. They gain 2 to become 2-. So we look at that, we're going to need 2 sodiums for every oxygen. Metals lose their outer shell electrons. Non-metals gain. So oxygen had 6 because it was in group 6. So remember that They don't want to pair up if they don't have to, so make sure that your 6 aren't 3 lots of 2. They're 2 2s and 2 separate ones. And then make it up to 8 with the dots. But each sodium did only lose 1, so we needed 2 sodium. So remember that the 2 now goes in front. Calcium with oxygen, calcium oxide. So you locate them in the periodic table. Calcium's in group 2, oxygen's in group 6. Group 2 lose 2, group 6 gain 2. Calcium oxide. So the metal doesn't have any outer shell electrons and it has a charge equal to its group number. The non-metal has 1 type of electrons equivalent to its group number, so 6 electrons. Make it up to a full shell with the other type, so in this case dots. That'll be 2 minus. We don't need to double anything up because 2 plus and 2 minus balance out. Aluminium oxide. Now aluminium's in group 3, so 3 plus, and oxygen is in group 6, so 2 minus. To make that formula, we have to go Al2O3. We need to get to 6 pluses and 6 minuses to balance the charge. Aluminium is a metal. It loses its outer shell electrons to become 3 plus. Oxygen is a non-metal. It gains. So remember, just like all the other times we've had oxygen, 6 outer shell electrons of its own. Make it up to 8 with 2. So 2 minus. To make the formula, we needed 2 of these aluminium ions and 3 of these oxide ions. And then our last one of these, magnesium nitride. So magnesium's in group 2, nitrogen's in group 5, so it needs 3 to get to 8. Mg3n2. So the metal loses its outer shell electrons and the non-metal gains. So nitrogen was in group 5, so 1, 2, 3, 4, 5. 1, 2, 3 minus. We needed 2 of these and 3 of these, and we've got magnesium nitride. This is a recap from GCSE with some maybe slightly trickier formulas. The dot and cross diagrams are not actually as important at A-level, it's just a memory step to help you remember how to come up with the formulas. What we've finally got on this little section is then about compound ions. So ions that are covalently bonded inside the ion but then ionically bonded to the metal or an ammonium ion. So what we need you to do now is just pause the video and see how many of the formulae of these what we call compound ions you can remember from the introduction pack. So did you remember that ammonium was NH4 plus, that hydroxide is an OH minus? Now you might have got a little bit confused by these Roman numerals. So what do these Roman numerals tell us? We've got 2 nitrates here. Now if I tell you that the nitrate that you probably remembered from your introduction pack was NO3 minus, right, we can look at these Roman numerals and say to ourselves, what must the 5 refer to? So let's just go back up to the top of the page. We've got a little bit of space. NO3 minus. Now, the 5 is telling us about the number of electrons that nitrogen is using in its bonding. Now, there's going to be a whole topic about this later on to help you understand it a bit further. But if this was plus, Roman numerals are always positive, if this was plus 5, each oxygen would be minus 2. We know that because oxide ions are minus 2. And that is how we get a minus 1 charge. Now, if the nitrate is going to be always is a 1 minus ion, nitrates are always a 1 minus ion, but have a plus 3 for our other nitrate 3 here. How many oxygens do you need to get from 3 to minus 1? So just doing some maths, how much do you need to take away from 3 to get to minus 1? Well, if you take away 1 oxygen, 3 take away 2 is not going to get me to minus 1, but if I take away a second oxygen, then I am going to get to minus 1. So the formula of this new type of nitrate 3 is NO2 minus. Now we're going to come back to this in another topic, so for now I don't want you to worry too much about it, but do see if you can understand where it's coming from. Cyanide is a new one, we haven't learnt that one before, that's a Cn minus. Now technically the minus really is actually on the C of this, but we tend to write ions like with the minus charges to the right, just like on the OH, minus technically on the O, the minus charge. Hydrogen carbonate, we know that one from before, HCO3 minus. And hydrogen sulfate, this is actually sulfate 6, I'm going to put that Roman numeral in there, HSO4 minus. Carbonate, you should remember a CO3 2 minus. Now we come to these Roman numerals again. Now the sulfate that you know is sulfate 6, it looks like this. So let's just have a look at that, SO4, all sulfates are always minus 2. So the 6 means that the sulfur was plus 6, and we can see that if we take away 4 lots of minus 2 from plus 6, we get to minus 2. But what if we had this other one, sulfate 4, so this time the sulfur was plus 4, how many oxygens would we need to take away to get to minus 2? So how many things, if I take away 1 oxygen, I've got to plus 2. If I take away 2 oxygens, 4 take away 4 is 0. So I have to take away 3 oxygens before I get to minus 2. Then we've got hydrogen phosphate. We know the phosphate ion is PO4 minus. This would be HPO4 2 minus, and this is PO4 3 minus. Okay, so now don't worry about too much about how I derived those formulae. If you're looking at those formulae, could you put together these ionic compounds? So sodium, what we're going to do is we're going to take each one. Sodium we know is in group 1. Hydroxide, we look up at the table above if we haven't remembered it. What would be the formula when you put those together? I'm going to leave that for a second because you're going to have a go at these. What calcium is in group 2? Carbonate, CO3 2 minus from above. Barium is in group 2. Hydroxide, OH minus. Calcium is in group 2. Nitrate 5, we're going to go up here, we're going to have a look. Nitrate 5, that's the one we knew before, NO3 minus. Ammonium, NH4, try not to fall into the trap of thinking that says aluminium. Chloride, Cl minus. So pause the video now and see if you can join these ions together to make the formula. Remember that we might need brackets, that the number's all going to hit the floor in formulae, so we're putting numbers down here, no big numbers, no changing charges. Did you get NaOH, calcium carbonate, CaCO3, barium, but hydroxide, you need 2 of those, so you have to put it in brackets. Calcium, you need 2 nitrates, so did you put the nitrate ion in brackets? And then ammonium chloride, you don't need any brackets. So putting this next one's name together, we've got the positive ion is a sodium here. So we're going to say sodium, and our negative ion is a hydrogen carbonate. Remember, it only has 2 parts to its name. So sodium hydrogen carbonate. All one word for the negative ion, 1 word for the positive ion. Potassium in group 1, K+. Sulfate 6, so go up and have a look. Sulfate 6, SO4 2 minus. Put them together, K2SO4. Ammonium, NH4+, hydroxide, OH minus, NH4OH. Sodium phosphate here, because we've got sodium ions and phosphate ions. The reason that we need 3 sodiums is because the phosphate ion is 3 minus. Ammonium, NH4+. Sulfate 4, so go back up and look. Sulfate 4 is this other one, SO3 2 minus. Now, the positive ion is only 1+, so I'm going to need 2 of those to balance the 2 minus. And then magnesium in group 2, phosphate, PO4 3 minus. So I'm going to have to go Mg3 brackets PO4 twice. Maybe you'll need to look in your recall pack and practice some more formulae, but everything we've just done in this video It was quite a long video, but it's all about ionic compounds. A lot of it you've done before. So we look at making ionic formulae, joining them together to make ionic compounds, dot and cross diagrams that you maybe did at GCSE, and then just some introduction of some new terms that you're going to come across again later and practice a bit later. But for now, can you, given those new formulae, come up with this kind of ionic formula? And just maybe write down to yourself, all nitrates are always -1 ions and all sulfates are always -2.